In enterprise AI, standard practice is request-level routing. The architecture dynamically diverts individual prompts to different large language models, balancing cost against raw reasoning power. While request-level routing is optimized for single-turn inference, it remains architecturally incompatible with multi-step agentic workflows. Agentic workflows function as stateful execution traces. The agent relies on an interleaved sequence of language model calls, tool executions, and memory retrievals to accomplish a single goal. This creates a granularity mismatch. Standard routers treat this long horizon execution as a series of isolated, independent queries. When treating a connected sequence of actions as stateless requests, the system loses the ability to optimize for task completion. It prioritizes localized efficiency over the end goal. We can see the failure mechanism by looking at a mid-task routing downgrade. A large model handles the initial steps, building specific context. If a simpler next step is diverted to a smaller model, that accumulated state is discarded. The smaller model fails. Lacking trace context, this localized routing decision triggers a global task failure. Success or failure in an agentic workload is a single delayed signal. You only observe the outcome when the entire task terminates. A final pass or fail grade cannot be accurately mapped back to a dozen independent, disconnected routing decisions made mid-task. To improve an agent's success rate, the unit of routing must match the unit of feedback. TraceRouter addresses this by shifting the routing abstraction away from the individual request and onto the entire task trace. When a new workflow arrives, an agent harness assigns a unique, persistent identifier. This locks the workflow to one backend model in an active task table. Subsequent queries bearing that ID bypass routing entirely, flowing directly to the assigned model. This sticky assignment ensures model identity remains constant, so accumulated context is never dropped midway through an operation. Routing tasks blindly leads to a policy that averages successes and failures. It fails to identify distinct performance regimes. TraceRouter employs a context classifier at admission. A regex scan sorts incoming tasks into coarse difficulty tiers before any language model is invoked. The system deploys an independent multi-armed bandit for each tier, allowing the router to learn the optimal model for specific contexts over time. Rather than relying on offline training data, TraceRouter uses cold start upper confidence bound exploration. This chart compares 3 exploration algorithms. UCB on the far left maintains a high and stable optimum. Injecting prior assumptions via a warm start suppresses necessary exploration, leading to unpredictable efficiency drop-offs in the epsilon greedy PAM.
Combining lightweight pre-classification with unbiased UCB exploration allows the router to dynamically map unknown workloads without requiring offline training pipelines. The advantage of this architecture is realized when the task terminates and the environment grades the final output. The system isolates 2 metrics, the graded accuracy of the output and the end-to-end wall clock latency. These variables are scalarized into a single delayed reward metric, calibrated by a defined preference parameter. Because the task ID preserved the connection, this reward traces backward to update only the specific context bandit that made the initial routing decision. This delayed feedback loop aligns the terminal reward with the initial decision. The system learns multi-step competence rather than optimizing for single-step guesses. The empirical proof of this architecture is visible in the Pareto frontier data mapping task accuracy against mean latency. This chart plots task accuracy against latency. Square markers represent the baseline small and large models. Mixing them tracks a straight line. TraceRouter's circular markers push past this interpolation line, operating strictly in the non-dominated interior. With a matched latency budget, task-level routing achieves 7 to 8 higher accuracy points than probabilistic mixing. Routing can even be faster and more accurate than exclusively serving the largest model. Weaker models burn turn budgets, failing tasks they cannot solve, which massively inflates the average latency. Intelligent trace-level routing shifts the cost-quality trade-off curve, enabling operational efficiencies that per-request routing cannot reach. Efficiency becomes more critical as deployments scale into heterogeneous pools of 4 or more distinct models. As candidate pools expand, manual heuristic rules and fixed complexity thresholds become increasingly difficult to tune. On Live Code Bench, TraceRouter, the circular data points, autonomously finds the optimal latency reward trade-off. In contrast, static routers often assign requests to high latency models that exceed timeout limits, hurting both latency and overall accuracy. Autonomous, bandit-driven exploration provides a mathematically sound method to manage growing multi-model infrastructure. Current routing paradigms treat complex, stateful AI agents as simple, stateless web requests, an approach that utterly fails in long-horizon workflows. To optimize a multi-step execution, the unit of routing must perfectly match the unit of feedback. For systems engineers building agentic workflows, the focus of infrastructural optimization must shift away from isolated prompts and onto continuous execution traces. Task-consistent routing serves as a structural prerequisite for deploying reliable, long-horizon AI agents at enterprise scale.